From prehistoric times to the present, mining has played an important part in human existence. Here the term mining is used in its broadest context as encompassing the extraction of any naturally occurring mineral, substances, solid, liquid and gas from the earth or other heavenly bodies for utilitarian purposes. The history of mining is fascinating. It parallels the history of civilization, with many important cultural eras associated with and identified by various minerals or their derivatives. The Stone Age prior to 4000 BC, the Bronze Age 4000 to 5000 BC, the Iron Age 1500 BC to 1780 AD, the Steel Age from 1780 AD to 1945, and the Nuclear Age 1945 to the present. Mining in its simplest form began with Paleolithic humans some 450,000 years ago, evidenced by the flint implements that have been found with the bones of early humans from the Old Stone Age. Our ancestors extracted pieces from loose masses of flint or from easily accessed outcrops, and using crude methods of chipping the flint, shaped them into tools and weapons. By the New Stone Age, humans had progressed to underground mining in systematic openings 2 to 3 feet in height and more than 30 feet in depth. However, the oldest known underground mine, a hematite mine at Bamboo Ridge, Swaziland, is from the Old Stone Age and believed to be about 40,000 years old. Early miners employed crude methods of ground control, ventilation, haulage, hoisting, lighting, and rock breakage. Nonetheless, mines attained depth of 800 feet by early Egyptian times. The abundance of minerals also provides a method of creating wealth. Minerals can be marketed on the open market, enabling the countries that possess them to obtain valuable currency from countries that do not. This generally results in the minerals rich countries being the great civilizations of the world, while the have-not countries generally suffer from a lower standard of living. In this chapter, we shall discuss about basics of mining and the geology of mines. The following modules will be covered: mining terminology, role of geology in mining industry, geological factors considered for the selection of mining method. There are many terms and expressions unique to mining that characterize the field, and thus it is advised to become familiar with all the terms used in mining, particularly those that are peculiar to either mines or minerals. The following three terms are closely related. First, mine, an excavation made in the earth to extract minerals. Second, mining, the activity or occupation and industry concerned with the extraction of minerals. Third, mining engineering, the practice of applying engineering principles to the development, planning, operation, closure, and reclamation of mines. Some terms distinguish various types of mined minerals. Geologically, one can distinguish the following mineral categories. Mineral, a naturally occurring inorganic element or compound having an orderly internal structure and a characteristic chemical composition. crystal form, and physical properties. The nature of mineral deposits are evident in the following terms. First, ore. A mineral deposit that has sufficient utility and value to be mined at a profit. Second, gangue. The valueless mineral particles within an ore deposits that must be discarded. Third, waste. The material associated with an ore deposit that must be mined to get at the ore and must then be discarded. Gangue is a particular type of waste. A further subdivision of the types of minerals mined by humankind is also common. These terms are also often used in the industry to differentiate between the fuels, metals, and non-metallic minerals. The following are the most common terms used in this differentiation. First, metallic ores. Those ores of the ferrous metals, that is iron, manganese, and tungsten. The base metals, that is copper, lead, zinc, and tin. The precious metals, gold, silver, the platinum, and the radioactive minerals, that is uranium, thorium, and radium. Second, non-metallic minerals. The non-fuel minerals ores, those are not associated with the production of metals. These include phosphate, potash, halite, trona, sand, gravel, limestone, sulfur, and many others. Third, fossil fuels, also known as mineral fuels. The organic mineral substances that can be utilized as fuels, such as coal, petroleum, natural gas, coal bed, methane, gisonite, and tar sands. The essence of mining in extracting mineral wealth from the earth is to derive an excavation or excavations from the surface of the mineral deposit. Normally, these openings into the earth are meant to allow personnel to enter into the underground deposit. However, boreholes are at times used to extract the mineral values from the earth. These fields of boreholes are also called mines, as they are the means to mine a mineral deposit. Even if no one enters into the geologic reams of the deposit, if the excavation used for mining is entirely open or operated from the surface, it is termed as a surface mine. If the excavation consists of openings for human entry below the earth's surface, it is called an underground mine. The details of the procedure, layout, and equipment used in the mine distinguish the mining method. This is determined by the geologic, physical, environmental, economic, and legal circumstances that pertain to the ore deposit being mined. Stages in the life of a mine. The overall sequence of activities in modern mining is often compared with the 5 stages in the life of a mine: prospecting, exploration, development, exploitation, and reclamation. First, prospecting. The first stage in the utilization of a mineral deposit is the search for ores or other valuable minerals, that is coal or non-metallic. Because mineral deposits may be located either at or below the surface of the earth, both direct and indirect prospecting techniques are employed. Second, exploration. The second stage in the life of a mine, exploration. Exploration determines as accurately as possible the size and value of a mineral deposit, utilizing techniques similar to but more refined than those used in prospecting. The line of demarcation between prospecting and exploration is not sharp. In fact, a distinction may not be possible in some cases. Exploration generally shifts to surface and subsurface locations, using a variety of measurements to obtain a more positive picture of the extent and grade of the ore body. In the third stage, development, the work of opening a mineral deposit for exploitation is performed. With it begins the actual mining of the deposit, now called the ore. Access to the deposit must be gained either 1. By stepping the overburden, which is the soil and or rock covering the deposit. to expose the near surface ore for mining, or second, by excavating openings from the surface to access more deeply buried deposits to prepare for underground mining. Fourth, exploitation. Exploitation, the fourth stage of mining, is associated with the actual recovery of minerals from the earth in quantity. The mining method selected for exploitation is determined mainly by characteristics of the mineral deposit and the limits imposed by safety technology, environmental concerns, and economics. Geologic conditions such as the dip, shape, and strength of the ore and the surrounding rock play a key role in selecting the method. Traditional exploitation methods fall into two broad categories based on locale: surface or underground. Surface mining includes mechanical excavation methods such as open pit and open cast, and aqueous methods such as placer and solution mining. Underground mining is usually classified in three categories of methods: unsupported, supported, and caving. The final stage in the operation of most mines is reclamation, the process of closing a mine and reconturing, revegetating, and restoring the water and land values. The best time to begin the reclamation process of a mine is before the first excavations are initiated. In planning for the reclamation of any given mine, there are many concerns that must be addressed. The first of these is the safety of the mine site. The second major issue to be addressed during reclamation of a mine site is restoration of the land surface, the water quality, and the waste disposal areas so that long-term water pollution, soil erosion, dust generation, or vegetation problems do not occur. Geology has the vital role to the mining industry because it helps to ensure that the minerals are efficiently extracted from the deposit for maximum profit, and to locate deposits of important minerals and determine whether the quantities are large enough to make mining economically viable. Typical work activities of geology in mining industry include mapping, recording, and compiling geological data in and around the mine, exploring, dating, and sampling mineral deposits, interpreting and mapping the geology of a mine, preparing and presenting data, checking the quality levels of materials produced for reserve assessment, classifying resources, assessing geotechniques, and updating detailed databases, etc. This provides the mining engineer with details of the location, its structure, and distribution of ore in a deposit. Furthermore, it delineates the ore reserves on which the mine's life depends, using geoscientific techniques to predict the grade and structure of ore bodies in unknown areas. It plays a crucial role in the optimization of ore body and is ultimately involved in the mining planning. Geology provides advice and expertise in the geological aspects of development and production in mine, pit, and quarry sites, in overseeing drilling and surface exploration programs, and also help to determine likely directions for future development. Working as part of a multidisciplinary team, geology makes the mining engineers to assure the quality of minerals, rocks, and gems extracted, as well as ensuring the safety of the extraction process. As mine geologists are often responsible for estimating the mine reserves, numeracy and computer literacy usually form a key part of the job role. Mining geology can be used in, first, determination of direction and depth of subsurface mineral deposit. Second, determination of persistence of coal seam at depths. Third, determination of true dip based on apparent dips. Fourth, determination of true dip and direction of the mineral in a quarry phase. Fifth, determination of vertical thickness of dipping mineralization in different directions. Sixth, determination of true dip, dip direction, thickness and distance of outcrop from the nearest borehole. Seventh, estimation of reserves in underground mine using borehole data. Eighth, alignment of adit, shaft and incline in a moderately dipping ore body and in a steeply dipping ore body. Ninth, mine planning. Geological factors related to mining. The geologic factors that influence mining methods selection are discussed in the following sections. First, lithology. The lithology of a rock until is a description of its physical characteristics visible at outcrop, in hand or core samples or with low magnification microscopy such as color, texture, grain, size or composition. It may be either a detailed description of these characteristics or be a summary of the gross physical character of a rock. It is the basis of subdividing rock sequences into individual lithostratigraphic units for the purposes of mapping and correlation between areas. Second, structures. Rocks often contain small scale structures smaller than the scale of an individual outcrop. In sedimentary rocks, this may include sole markings, ripple marks, mud cracks and cross bedding. These are recorded as they are generally characteristic of a particular depositional environment and may provide information on paleocurrent directions. In metamorphic rocks associated with the deeper levels of fault zones, small scale structures such as asymmetric bundles and microfolds are used to determine the sense of displacement across the zone. Third, porosity and permeability. Porosity of a rock is a measure of its ability to hold a fluid. Mathematically, porosity is the open space in a rock divided by the total rock volume, that is solid plus space or holes. Porosity is normally expressed as a percentage of the total rock which is taken up by pore space. For example, sandstone may have 8% porosity. This means 92% is solid rock and 8% is open space containing oil, gas or water. Permeability is the property of rocks that is an indication of the ability for fluids, that is gas or liquid, to flow through rocks. High permeability will allow fluids to move rapidly through rocks. Permeability is affected by the pressure in a rock. Fourth, mineralization. Mineralization is the hypothermal deposition of economically important metals in the formation of ore bodies or lodes. The term can also refer to the process by which water-borne materials such as calcium carbonate or calcite, iron oxide, that is hematite or limonite, or silica, that is quartz, replace organic materials within the body of an organism that has died and was buried by sediments. Fifth, topography. The study of surface shape and features of the earth and other observable astronomical objects including planets, moons and asteroids. It is also the description of such surface shapes and features, especially their depiction in maps. The topography of an area could also mean the surface shape and features. Geological factors considered for the selection of mining methods. First, surface mining. Ore reserves suitable for surface mining can be classified initially as A. Relatively horizontal stratified reserves with a thin or thick covering of overburden. B. Stratified vein type deposits with an inclination steeper than the natural angle of repose of the material so that waste cannot be tripped inside the pit. C. Massive deposits, deep and very large laterally such that dumping of the waste within the pit is not possible. Of all the variations of surface mining methods available, let us discuss the three most common methods. First is strip mining. Strip mining is ideally applied where the surface of the ground and the ore body itself are relatively horizontal and not too deep under the surface, and a wide area is available to be mined in a series of strips. Terrace mining. It is a multi-benched sideways moving method. The whole mine moves over the ore reserves from one end to the other, but not necessarily in a single bench. The number of benches used is usually a function of the excavation depth and type of machinery used, typically between 10 to 15 meter bench height and 1 to 32 benches in the terrace. Third is open pit mining. This is the traditional cone shaped excavation, although it can be any shape depending on the size and shape of the ore body. That is used when the ore body is typically pipe shaped, vein type, steeply dipping, stratified or irregular, although it is most often associated with metallic ore bodies. It can be used for any deposit that suits the geometry, most typically diamond pipes. The excavation is normally by rope or hydraulic shovels with trucks carrying both ore and waste. Drill and blast is most often used, which makes the process cyclic. Benches in the stack have a steep face angle, whilst the stack and overall slope angles are flatter, thereby helping to prevent slope failures. Each pit slope can have a different angle according to the requirements of the design, with or without haul road, geology, etc. Second, underground mining. The mining method selected is determined by the size, shape, orientation and type of ore body to be mined. The ore body can be narrow, vein or massive. The width or size of the ore body is determined by the grades as well as the distribution of the ore. The dip of the ore body also has an influence of the mining method. For example, a narrow horizontal vein ore body will be mined by room and pillar or long wall method, whereas a vertical narrow vein ore body will be mined by an open stoping or cut and fill method. Further consideration is needed for the strength of the ore as well as the surrounding rock. An ore body hosted in a strong self-supporting rock may be mined by an open stoping method, and an ore body hosted in poor rock may need to be mined by a cut and fill method, where the void is continuously filled as the ore is removed. In this chapter, we studied basic terminology used in mining, role of geology in mining industry, and various geological factors which help in mining method selection. We can conclude from our lesson that economic mineral deposits are extremely variable in their mineralogy and grade, and the geologist must be able to identify or have identified for him or her every mineral in a possible ore body. This will help them to assess the full economic potential of any material to be mined from it and prevent them overlooking the presence of additional valuable constituents or deleterious substances that may render the deposit unworkable. If mining projects are to progress successfully from the exploration and evaluation phase to full-scale production, then exploration geologists must appreciate the criteria used by mining and mineral processing engineers in deciding upon appropriate mining and processing methods, and also by financial fraternity in assessing the economic viability of a proposed mining operation. There are many techniques now available for comprehensive mineralogical examination of mineral samples. However, such investigations must be quantitative as well as qualitative. Grain size and shape, relative mineral amounts, and the manner of interlocking must be determined. Thank you very much.